Hello guys, this is Saddam Cap and today we are going to discuss few important things. First of all, let me just start with that what we have covered so far in IIT JAM syllabus. So it's not IIT JAM 2023, it's already done. So we are going to prepare for 2024. So what we have done in this channel so far is that we have completed partial derivatives, Jacobian, imperfect and perfect differentials, Taylor series expansion and many more important topics in the partial derivatives. And the course is very straightforward and all the topics has been done within 15 or 20 minutes, so you can check it out. And now we are going to start the new topic on calculus of single and multiple variables. Okay, what is the meaning of it? Means that we are going to start with first of all multiple integrals, that how we can do integrals which is depending on more than two variables. That is the thing we are going to discuss so far. So let's get started our video. सो टुडेज टॉपिक इज मल्टीपल इंटीग्रल्स। तो आज हम शुरुआत करने वाले हैं अपने वीडियो की मल्टीपल इंटीग्रल्स से। तो आपको ऑलरेडी पता है कि व्हाट इज द मीनिंग ऑफ इंटीग्रल्स। इंटीग्रल्स में हम क्या करते हैं, एक ऐसा साइन लगाते हैं एंड वी हैव सम काइंड ऑफ फंक्शन व्हिच इज मे बी डिपेंडेंट ऑन वन वेरिएबल एंड हियर इज द डिफरेंशियल ऑफ दैट वेरिएबल। ठीक है ना। तो एफ ऑफ एक्स क्या बोलता है कि जो भी फंक्शन है आपका वो इस इंडिपेंडेंट वेरिएबल पे डिपेंड करता है और ये इंडिपेंडेंट वेरिएबल का हम इंटीग्रेट कर रहे हैं। So basically, what is this integration? Integration is basically the inverse of derivative. If you take an inverse of any derivative, then you will end up with the integrals. And we already know that how this integral works. So just give me the few, I'm giving you some kind of few, simple examples that how we can take the integrals. That suppose you have the independent variable x to the power n, dx, and n is some kind of constant, then we are ending up with that x to the power n plus 1, and here then simple n plus 1 and there is some kind of integration constant। ठीक है ना। तो अगर मैं इसका अगर सपोज कि मैंने ये बोला कि ये जो है वो क्या होता है एंड इनवर्स होता है डेरिवेटिव का, तो एक बार अगर मैं इसका अगर डेरिवेटिव लूंगा तो क्या मुझे ये वाला फंक्शन मिल जाएगा? यस। सो इफ आई एम टेकिंग द डेरिवेटिव इनवर्स ऑफ दिस डेरिवेटिव, देन व्हाट विल हैपन, x to the power n plus 1 over n plus 1 and then there is a c। so what will I get over here, that if I am taking the derivative of this thing, h to the power n plus 1, then n plus 1 minus 1 over n plus 1, and derivative of any constant is going to be 0. So there is nothing over here. N plus 1 cancel, this 1 cancel, and then I have this function. So I can say that this x to the power n has the derivative or integral this one, and this integral has the derivative this one. So this is how the integral and derivative works. We can say that the integral is a antiderivative, or what can say that the because derivative is what we are basically defining, and after that there comes an integral. So first of all, we have to understand more about this integral, that how this integral basically working at something. For example, when you are trying to do the integral of any function, so what you need to define is that you need to define some limits, that at what limits or at what domain you are going to integrate these functions. Okay, so for example, this is the function which is represented by some kind of particular curve, and you are trying to integrate this between the limits of a and b, and this limits is defined in x. So this is your independent variable over here, x, and this is y, and y over here is that, let us say this is f of x and some kind of curve. So what you are doing basically is that you are taking here there are two things. So you can what you can see over here, that y times dx. Okay, so this y is basically f of x. So what we can do here over is that what you can say that this integral is basically giving you the area under the curve. What is this area under the curve? Means that when you are trying to find the integral, what you are basically doing is that you're trying to understand that what is the integral, what is the area of under this curve. Okay, so how we can decide that, how we can find the area of this thing. So in order to find the area of any particular kind of curve, we are going to divide into a very small pieces in such a way that these small pieces are making a rectangle. So you can see that this y times dx, it means say that there is some kind of length over here and there is something kind of width. So this is the dx. So suppose that for any kind of curve, if you can divide this curve into a small pieces of rectangle, then you can, you can now use the area of this rectangle, and then you can easily add those rectangles to find the area of this curve. And this is how you are going to understand that what could be the integral of this particular curve, isn't it? So how we can do it? We can do by taking some kind of, if you're starting from a, so you can take that, okay, this is, let us say, a plus delta x, and similarly a plus 2 delta x, a plus 3 delta x. What is this delta x is doing? Delta x says that the interval between two x's means that, let us say, there is one x1 over here, and this is, let us say, x0 over here, then delta x is x1 minus x0. So this thing is more or less same for each and every interval. And if you try to jump from one interval to another interval, this delta x is but adding and adding and until you reach this b. So what's going on over here is that you are just starting from here and you are reaching towards b by going from just simple steps, and it is called the stepping over it. Okay, and as you are going over here and over here, the function is also changing. Therefore here you can see that we are dividing this f of x, let us say f of x, let us say x1, this would be f of x2, and so on. And now we are adding everything, and then this is how we are finding the area of this particular integral, isn't it? So now when something is involving, for an example, let us say sine of x and dx, then you will know that this is cos of x plus c. And if you have any problem evaluated the integral on different kind of things, then you can also go your class 12 syllabus and do the integral chapter because there they have a very extended chapter up to, let us say, up to exercise 10, and you can try out the integrals. And if you don't know, if you don't understand any concept, you can comment on the, you can comment here, and I'm going to discuss all those problems. Okay, so now the problem over here is that how we can do the integral if a function is depending on both fx and y, and therefore we need to take a derivative, or we need to take an integral on dx as well as dy. Okay, so we have already found out that if you take a derivative, you want to take a derivative of, let us say, fxy, and let us say it is a total derivative, then you can, what you can do is that df of x can be written as delta f over delta x when your constant y, and again you can take a complete derivative, again delta f over delta y with respect to constant x, and you can take a total derivative in y. Okay, so this is how we can express this total derivative of the function. Understood? So now over here that this function is depending on fx y, and the integral is over del x and del y, so therefore there are two integral variables, therefore we need to apply here two integrals. The problem over is that how we can now decide, how we can evaluate this integral. तो ये एक सबसे बड़ा important factor होता है कि हम कैसे figure out करें. Now first of all we need to understand that what is the meaning, what kind of geometry you will get. So in case of one variable, it was quite easy one, that okay, this is how we can find it out. There is only one curve, is one dimensional, and we are just evaluating a value at some particular one. So suppose you are increasing the dimensionality, what will happen? So when you are increasing the dimensionality of something, then what you are getting, that the one dimension will become now have kind of surface kind of structure. It means that there is a one dimension of line, and now if you are taking this line and you are making it such a thing, then what you are observing is that there is a circle. Circle cannot exist in one dimension, it has to exist in two dimensions. Now circle does not have surface, but what happens if you turn this into a disk? Okay, disk is also, you can say that it is a two dimension. If you remove the thickness, then it has the surface, isn't it? So it has the surface, and surface, you can say that there is x and there is y, and you are looking from the z and you are seeing the surface. So what is this integral? This integral is basically you are doing the surface integral of any particular function, that is dx and dy. Now how we can achieve this integral? So the way to achieve this integral is that you already know that this is a kind of surface integral, and how we can do. Now here you can see that this surface integral is something like the two parameters, and these two parameters are multiplying, and you say this is giving you the area of the flavor. So whenever we have the surface, we have the area. For an example, let us say the 3D example of the surface is the sphere, and you can see that the sphere has 4 pi r square. This 4 pi r square is giving you that for three-dimensional object, you got the two-dimensional surface, that is 4 pi r square. On the other hand, if you have the cylinder, then again in the cylinder, this is again a surface, the curved surface, and this curved surface is coming out to be pi r into h, isn't it? So sorry, not pi r into h, it is 2 pi r into h. Okay, so here you can see that this is the length, and the dimension of this here is length, and this is length squared, therefore it is again a two-dimension, isn't it? So that is the very interesting way, that whenever you have a three-dimension kind of thing, then the 3D minus 1D is giving you the surface of that particular dimension, isn't it? That's why when you have this dx and dy, then there is an area, and this is associated with the area of the geometry of maybe some particular kind of 3D type of geometry, isn't it? So now what we can do, okay, so suppose you have some particular kind of function, let us say f of x, y, and here maybe you have one particular over here is that x, and let's say y. So if you want to draw something, some kind of surface over here, then you are looking from above, and you have this particular kind of surface in xy. So the way to make this thing is that, okay, you have this x and you have y, and you are drawing some surface over here, and you are looking from the above or maybe some kind of z. So now what you can see over here, that if this kind of thing happens like x, y, and let us say dx or dy, there are two ways to find this integral. It means that when you are doing the evaluating the integral over here, then your y becomes constant. As you have when you may see my videos on limit, that when you try to evaluate the limit of let us say the function which is depending on two variable, so there is a path that if let us say x approaches to a and then y approaches to b, so there is a path that first we are going to evaluate the limit at x a, and then we are going to limit at b, and similarly we can find this f of x y as y to b and x of a. So we understand that, okay, this function is not a discontinuous, the limit is exists, it means that this function is path independent. So what we can do here over here is that first of all we are going to treat this function and in such a way that we are first evaluating the integral with dx by assuming that y is your constant, and then we are going, when this is done, and let us say you will get some g of x y, and now there is nothing like y, everything will become y. Okay, now it is reduced to one dimension, and then you can evaluate the integral over here. So when you do this integral, then your lower limit is a, and another lower limit will be, so another higher limit would be y. Okay, so everything you are now mapping everything x in terms of y, and then when you will evaluate this thing, everything will become y dependent. Now it does not depend that the upper limit y has to be something like always y, it may be some kind of constant. So it means that when you are evaluating this integral, that is dx, then you may say that okay, this integral is already done and there is nothing into it, and then you can evaluate whatever the thing is going on. For example, I'm giving an example. For an example, let us say x into y, and there is dx, let us say dy. Okay, so first you are evaluating this integral, and let me just use over here that this is 0 1 by half, and let us say 0 into 1. So you see that this integral, if you are doing at particular x, then your y is constant. So you may say that 0 to 1. Over here you will have x square by 2, and you have to put the limit over here 0 to half. Okay, so now whatever you, and your y is over here, and there is dy. So now your x is done and y is already independent. So x is done, so you can say that okay, this will be like 1 by 4 and this is 1 by 8, and 0 to 1 y dy. So this would be like 1 by 8 y square by 2, and if you put the limit over here 0 to 1, and then this is 1 by 16, 1 minus 0, so 1 by 16 is the answer. So this is the very most simple integral, that if your y is simply the whatever the integral first you have done, if the limits are in the constant thing, then it is very easy one, no problem. Just you can also rewrite this whole thing like, okay, I am just doing this x into dx as 0 to half, and 0 to 1 y times dy. I'm going to evaluate both things separately, and that is done. but not all the cases are this way. Therefore, order is very much important. So f of xy, therefore dx and dy. So if this is the case, then what you can do over here is that whatever the limit, then you have to, there is something y and there is some limit, let us say some c, and this limit would give you something like, let us say, d. Okay, so this is how we are going to achieve this integral. So now when we are doing this particular limit, what is the meaning of it? So let us say there is, we have dx and dy. So whenever we have surface, okay, let us say this is a surface, so this is y and this is x, so we can say that let us say this is some kind of an assumed line. So here you have one particular curve, let us say y1, and this is some particular curve, let us say y2, and first you are taking an integral with respect to dx. It means that your y is fixed. So what you can say that from here 0 to y, you are taking some kind of width over here, and this width has delta y, which is again constant, and you are taking the integral between these two limits over here. Let us say this limit 1 is x1 is equal to a, and there is one particular limit over here is that x2 is equal, let us say that is, you have already assumed that is y or something. Okay, so now once you are done over here is that now you can stretch this thing. Once you are done, let us say the integral of this will be c to, let us say, d, and this is, let us say, g of y and d of y. So the next step would be that you are now stretching this thing over here and over here. So what you will find that I am going to take an integral over here to over here, and then this will give you the entire surface, isn't it? So this is going to give you the complete integral. Now, similarly, what I can also take, I hope it is clear to you. So suppose there is another way to visualize it. Suppose there is some kind of surface, and again I have x and y, and what I can do here is that there is some kind of imaginary line over here, and whatever it is. So for an example, this is an integral. This is an integral x comma y. Instead of y, I have first dy and dx. So what is this thing? So my x is now constant. So for an example, I'm coming, this is my 0 over here, and I'm coming like this side, and I'm gonna fix this dx. That okay, this is my some width, this is delta x is fixed, and this dy is varying. So here you have the little rectangle over here, then you are taking an integral over here and over here. So once at particular delta x your dy is finished, then you can say that okay, this is going to happen like a of x. Then you are, what you will get here over here is that everything with the g of x and x, and then maybe some particular limits and so on, and then you can stretch everything back over here to over here. Okay, so it is like that something is constant, and then you are stretching everything over here. Similarly, this can be, this same thing can be done for the third, triple kind of integral. Let us say f of x, y, and z, and you have delta x, delta y, and delta z. So if all the limits are constant, then this integral is very easy. If it is not, then once you have to fix this dy and dz. Again, you have the second integral. Then you're gonna fix something, and then you can evaluate and then evaluate. So it's like that, partial derivative, that whatever the number of the variables, we don't care. First of all, we are going to fix one thing, and then we are going to evaluate the another thing. So this is how we have to proceed to determine the multiple integrals. Okay, so there are a lot of problems, and you can easily try. For an example, I am giving you very simple flavor of how to do this. 0 to x, let us say 0 to 1, and you may be here x square plus y square some alpha, and let us say dA. So this is kind of maybe in xy plane. Okay, so suppose this is x square y square. So again you are saying that it's kind of circle. So dA would be like dx times dy. So whenever you have this kind of dA, it's giving you that dA is equal to dx into dy. So I'm going to take this 0 to x square plus y square, and now since already they have given this one, so I am going to write over here dy into dx. So my first of all x is constant, and whenever we take the integral with respect to dy, I'm going to get everything in terms of x. So how? So over here you will get x square y plus y cube over 3. Let's say that alpha is gone, or maybe alpha is there, no problem. Okay, so here you can plug over here 0 to x and now dx. So 0 to 1, and your variable was y. So whenever you put y, so you have to replace this y. Okay, you are not supposed to replace this x. So what you can do over here, that x square and then here x and plus x cube over 3 times alpha, and if you put 0 then everything will become 0, therefore I don't care about it. Okay, so here you can see that x cube plus x cube over 3 into alpha and then the x, and therefore everything is now set. X4 over 4 plus x4 over 12 into alpha, then 0 to 1. If you put 0, everything will be 0, and if you put 1, therefore it will be 1, 1 by 2, 1 by 12 times alpha. So this is how you will figure out that what is the solution and so on. Okay, so that is a very interesting scenario, that how we are evaluating all these things and how something is coming out. So you can try various things, and now in the next time we are going to discuss that if you change your coordinate from x comma y to r comma theta, what will happen. This is the again a two-dimensional integral. Suppose I have x, y and z, and I'm going to integrate in the sphere kind of category. So we are going to discuss the area integral in the polar coordinate, as well as we are going to discuss the integral over the spherical coordinate. So that is the thing for the next video. Please subscribe my channel and share it to your friends. Thank you very much. This is Saddam Cap signing out.